Hi all, this is Sangeeta from VSP Engineering College Karur. As a continuation of lecture series on the fluid mechanics, in this lecture we will be discussing about dimension analysis and model studies. We can see the difference between the two terms, which is the prototype and the model. Prototype is of real world scale and it is massive in size, which requires high cost and it is a time consuming one, and it also leads to catastrophic failure risk, whereas model is of reduced scale of the prototype one, and it is very cost effective and safe for testing. So these are the basic definitions of prototype and model. And in this lecture, we can see how fluid physics helps in the miniature model to predict the massive prototype. So there are three basic dimensions for every component which is listed here. That is mass, that is the quantity of matter, that is the amount of matter which is represented by the symbol called m. And we all know the general term length, which is used to measure the dimensions. That is spatial measurement, and the next one is time, which is the temporal measurement. So these are the three basic fundamental dimensions every physical fluid property has to process how matter the complex forms. It is built from these basic dimensions, and as an example we can see related to velocity, it is they have given us L by T, that is usually velocity we will denote it as the unit is meter per second. So meter they are expressing in terms of L, which is spatial measurement, and per second it is expressed in terms of T. So it is given as L T power minus 1. So next acceleration they have given us L divided by T power T square. It can be written as L T power minus 2. So these are the basic equations for a dimensional analysis, which we will be seeing in the upcoming slides. And the next one is dimensional homogeneity. So here we cannot equate apples to oranges. That will not be considered as homogeneity or equal. We have to equate based on a physical relationship must be dimensionally identical on both sides. That is, left hand side dimensions for a particular component or a prototype or a model should be equal to the right hand side dimensions of the particular component or prototype or model. For example, here we can see the worked out example of the equation V is equal to U plus AT. So V, you all know, that is final velocity. That is as we have seen in the previous slide, it is given by L T power minus 1, which is called meter per second, and it should be equated to the right hand side dimensions U plus AT, where U is the initial velocity, which also has the same dimensions L T power minus 1, and acceleration, as we have seen in the previous slide, it has the dimension of L T power minus 2, that is meter per second square, and T, which denotes the time, which is denoted by capital T as a temporal measurement. So balancing on both sides, we can see that is the left hand side dimensions are equal to the right hand side dimensions. If this concept exists, this is called as dimensional homogeneity. As for an example, we have solved a very simple problem, but in the practical or questions, you may get some tedious questions, which we'll be seeing in the upcoming slides. And what is the toolkit? And we have a toolkit for defining the dimensional homogeneity, and dimensional analysis reduces a complex system of many physical variables into a smaller and manageable set of dimensionless groups, simplifying laboratory testing. For example, in the figure, you can be able to understand that so though we have many number of dimensional physical variables, raw physical variables such as velocity, density, viscosity, diameter, initial velocity, final velocity, gravity, acceleration due to gravity. So likewise, the entire parameters and all the parameters can by going through the dimension analysis tools, they can be expressed in terms of simple structured dimensionless parameters, so that we can be able to easily uh, develop prototype and models. Okay. So the first method for dimension analysis is Rayleigh's method, that is called as exponential approach for systems with a limited number of variables. So first one is the we have to formulate, express the dependent variable as a function of independent variables, that is x is equal to f of y comma z, and the next step we have to assign powers to that dependent variables. For example, x is equal to k dot y power a and z power b. So write the relationship as an equation with unknown exponential powers. And the next step is substitution. Replace all the variables with their fundamental dimensions m, comma l, comma t. So they have given an example, and we have to equate, use dimensional homogeneity to equate the powers of m, l, t on both sides to solve for a and b. So this is the process involved in Rayleigh's method, as it is denoted that it is useful for limited number of variables or physical quantities. And the next method is Buckingham's pi theorem, and this gives you the robust solution for complex systems, where Rayleigh's method becomes mathematically unwidely used. If there are n variables in a physical phenomenon and these variables contain m fundamental dimensions, then they can be grouped into n minus m dimensionless terms. This is the definition of that theorem, which indicates the three components called n variables and m fundamental dimensions and n minus m dimensionless terms. So n denotes the total number of physical variables. Example v, rho, mu, d and g, which is equal to 5. And m denotes the number of fundamental dimensions, as we have discussed earlier. It is only 3, which is called as mass, length and time. So the resulting number of dimensionless terms is, we have to subtract both the n and m, that is 5 minus 3 is equal to 2. So how many number of pi terms we will get means, that is pi 1 and pi 2 to pi terms. So this is the method for solving Buckingham's pi theorem oriented problems. That is for complex systems we can use Buckingham's pi theorem, and for simple variables and systems we can go with Rayleigh's method. And when we can go for Rayleigh's method and what are its limitations, we can see now. It is a variable limit, that is, it is best for only 3 to 4 variables of maximum. And whereas in Buckingham's pi theorem, it can handle an unlimited number of variables. Next, it is a mathematical approach. Rayleigh's method solves for unknown exponential powers, that is a comma b comma c, whereas in Buckingham's pi theorem it constructs independent dimensionless pi groups, that is pi 1, pi 2, like that. And in engineering application it is used for simple and highly isolated fluid phenomena. And in Buckingham's pi theorem, they are useful for complex real world fuel dynamics, that is full spillway analysis. And what is the important note we have to take here is, if the variable count, that is physical quantities or the system variable count, exceeds 4, Rayleigh's equation becomes unsolvable. And in such situations, we can go for Buckingham's pi theorem for solving complex engineering problems. And dimensionless parameters. We have some numbers which are dimensionless parameters. That is, in the universal language of fluids, by stripping away units, we can create ratios that remain identical regardless of scale. Reynolds number is the ratio of inertia force to the viscous force. It is crucial for pipe flow and is denoted by the symbol Re. Froude number is denoted by the symbol Fr. It is the ratio of forces, inertial forces to the gravity forces, and it is crucial for open channel flow or spillway flow. And Euler's number is the ratio of inertia force to the pressure force, which is denoted by the symbol EU. If Reynolds number of model is equal to the Reynolds number of prototype, that is, the fluid behavior is identical. Even if one is a tiny lab setup and the other is of a massive dam. With that is, when comparing a model and a prototype, if the Reynolds number of both the systems are same, the even if it is of massive in size, one is of massive size and another is of smaller in size. So these numbers play a vital role in the dimensional homogeneity analysis. The next one is achieving similitude. And similitude means that is the true similarity between a model and a prototype requires matching physics across three consecutive layers. First one is geometric symmetry, and second one is kinematic symmetry, and third one is dynamic symmetry. The physical outline and contours of the spillway, that is length, width, and depth scale, are exactly matched for a model and a prototype. It is called as geometric symmetry. And the next one is kinematic symmetry. If the flow lines and the velocity vectors are superimposed, time and velocity scale proportionally. And dynamic similarities, force vector interactions, all homogeneous interactions, or strictly proportional. So this is with regards to similitude. And engineering applications related to model and prototype. As you can see in the image, it is clear that that the laboratory testing for a model, we have to use scaled forces and observe the fluid behavior and measure the dimensionless parameters which we have discussed earlier, that is Reynolds number, Froude number, and Euler's number. And then the real world construction, that is a prototype, we have to go with the scale up of the laboratory models, and follows similitude laws and dictate final structural implementation. So this is with regards to applications. Model typology. We have seen that models are essential in dimensional homogeneity analysis. And there are two types of model, that is distorted model and undistorted model. In undistorted model, that is the geometric similarity is perfectly maintained. Horizontal and vertical scales are exactly same. That is LH is equal to LV, and it is ideal for spillways, pipes, and enclosed structures. Whereas in distorted model, geometric similarity is intentionally broken, and the scale is made larger than the horizontal. That is, LH is not equal to LV, and it is applied in the areas of rivers, harbors, where stored scale ratio would result in water depth too shallow and accurately due to surface tension interactions. The last one is the replication of the entire unit, how it is discussed. The first one is we have to define the physical variables, that is, example, viscosity, density, diameter, Poisson's ratio. And the next one is we have to apply the fundamental dimensions and break down into M, L, and T, and we can construct the model and test prototype. And next we have to, third step is we have to execute Buckingham's pi theorem, that is we have to identify the number of pi terms, n is how much, m and n minus m terms, and establish similitude, that is whether geometrically similarity, kinematic similarity, and dynamic rates. And we can construct the test and physical model, and whether distorted model or undistorted model. Distorted model is, that is, LH is equal to NV, and in undistorted model the LH is not equal to LV. And the purpose of this study is to master dimensional analysis so that the civil engineers can safely and accurately predict monumental forces of nature using nothing more than mathematics and miniature setups. So this is with regards to Unit 3, and we can see in the upcoming sessions related to Unit 4. Thank you.